And if we have our velocity measured in meters per minute, and time is in minutes, of course, and number 4 here says let A denote the acceleration of the particle, and it says is there guaranteed to be a time in the interval 0 to 12 such that the acceleration is equal to 0? Okay? So ultimately, again, do we know for sure that the acceleration would be equal to 0? Keep in mind that the acceleration would be the derivative of the velocity here. Right? And if we look at our values here, notice that we go from 0, -3, we go up to 2, 2, we go to 5, 3, we go to 6, 5, we go to 8, 7, and then we go back to 12, 5. Okay? So ultimately we're increasing as we approach time 8, but then after we get to time 8, what happens? We're decreasing. So if this is a differentiable function, which it is, says it's differentiable, then what should we expect then? What must have happened if we're going up and then all of a sudden now we're going down? We must have had a maximum. True? And then what really guarantees it though is that these 2 points right here, what would be the slope between these 2 points? 0. So remember, like we drew yesterday, if we had a slope between 0, the mean value theorem guarantees that we'd have at least 1 point between these two where the slope would be equal to 0. Okay, where the slope of the curve is equal to the slope of the 2 endpoints. So if we use these two as our 2 endpoints, okay, show that the slope was 0, which we could certainly do, then the mean value theorem would guarantee that somewhere between these two, okay, that the derivative is equal to 0. What else? Worksheet 2. Alright, how about example 2 from worksheet 2? We had, instead of a numerical, instead of a table, we were given a graph of the velocity instead. But questions on this one? Elizabeth? Says what is the average acceleration of the particle from time 2 to time 4? Ultimately, the average acceleration, remember, is the change in velocity over the change in time. So if we have the velocity graph here, if we have the velocity at 2, the velocity at 2 looks like it's at about 9, it looks like. True? So the velocity would be 9 there. And at 4, looks like the velocity is at 6. So the change in the velocity would be -3, from 9 to 6. And then the change in time would be 2. So it would be -3 over 2. And that would be our average acceleration, change in velocity over change in time. And remember, think about why, from another standpoint, that makes sense in terms of being an acceleration when we do that calculation. Okay? When we do that 6 minus 9, we're subtracting something that's a velocity, which is feet per second, and we're dividing that by seconds. So ultimately, what unit does that give? It gives feet per second squared, which is an acceleration, isn't it? So again, average acceleration is just a change in velocity over the change in time.
For number 1, how do you explain your answer?
Well, ultimately, if we want to know when is it moving left or right at 4 seconds, the velocity is 6, like we said a minute ago, right? And what is 6? Positive or negative? It's positive, so it'd be moving in a positive direction. So if this was a left and right motion problem, then it'd be moving in the positive direction, which would be right. So remember, the sign on the velocity gives the direction.
And if it's crossing the x-axis where it crosses is at rest?
If the velocity is 0, then it would be at 0, or only that instant, and it's changing directions generally. Or it could come hit it and go back up, and then be positive, positive, but at rest for that one moment. Yep. What else on the graphical question? Okay, on 5, and then in the last problem, we calculated that the slope between those 2 points in question was -3/2, true? Okay, so since the slope between the 2 endpoints is -3/2, does that guarantee that there's a point between those 2 times, 2 and 4, where the derivative equals -3/2? If you look at the picture, is there a point where the derivative equals -3/2? I mean, the derivative's positive over here, and the derivative's negative here, but it's much bigger than -3/2. So why is there how come the mean value theorem doesn't hold here then, like it did in the last problem? What is it about this function?
Because it's a corner.
And it's a corner, it's not differentiable. Okay. The mean value theorem only guarantees the derivative equals the slope between the endpoints if the function is differentiable. So that's why the mean value theorem does not hold in this particular instance. What else? Number 2 here. There was a number 6 on that. Questions about that one? Otherwise, how about number 3, the example 3? We're given the actual equation. Well, remember the total distance here would be the integral of the velocity, the absolute value of the velocity, but do we have the velocity given? So ultimately we found in number 3 that the points where the particle changed directions, okay, were at times 1 and 3. We find the velocity and we set it equal to 0, we get 1 and 3 for our 2 points in question. Okay, so that means that 1 and 3 were changing directions. So ultimately if we did the position at time 0, we'd be at 11, wouldn't we? If we put a 0 in, we'd be at position 11. Okay. And then ultimately, we know that our velocity is positive if we did the analysis here. And so at time 1, we're going to be at 15, so how far did we travel if we went from 11 to 15? We went 4. And then from 1 to 3, our velocity is negative, so that means we're going backwards, but distance traveled wise, we would have went from 15 to 11, so that would be another 4. And then ultimately, once we get to 3, we go positive again, and from 3 to 5, we go from 11 to 31. So those are our positions in question, so we went another 20. So displacement-wise, okay, it would just be the 20, because we went 4 and then 4 back, and then another 20. Okay, but total distance would have been 4, 4, and 20, so it would be a total of 28. So if we have the position function, okay, we can just find where we change directions, and we can just calculate what is our displacement on each of those different time intervals. What else? And example 3 here. Okay. How about worksheet 3, first page here? Especially the bottom part right here. Questions on how they got what they got on these? You didn't print your sheet out like I gave you? Tell them. Positive, increasing. So this one would be increasing, positive. And this one's increasing. Alright. Next one, in this graph, you can see that the velocity is negative. We have a picture of the velocity, so in terms of positive or negative, it's going to be negative. The increasing and decreasing, we can see that it is decreasing. So because the velocity is decreasing, we know the acceleration is negative. Remember, the acceleration is the slope of that curve we're seeing there, right? So if we have a decreasing velocity, the acceleration would be negative. And then it says by examining the graph of the speed in the table of values, we can conclude that the speed is, however, increasing. Because if you filled in your speed graph on the right, what is the speed relative to the velocity? It's the absolute value. So all your speeds are 1, 2, 4. The speed is increasing then, isn't it?
Won't speed always be increasing?
Not necessarily. It's not in this graph here, is it? If you did the absolute values of these, what's going on with your speed there? Speed would be decreasing, wouldn't it? Okay. So in a graph like this, it says the velocity is, first one is positive or negative.
Negative.
So velocity is negative and increasing. So the velocity is negative and increasing, that would be this picture. Because the velocity is increasing, we know the acceleration is positive, and by the table of values we can see that the speed is increasing. Let's see. Nope, I lied. Decreasing. The opposite of what I just said. So, what I said the first time.
Yeah.
Speed would be decreasing. These values on the right should have been 16, 8, 4, 12, 4, 2, and so on. So those are decreasing. Questions on situation 3. All right.
Do they have these type of problems on the AP test?
Very well could. So in the final situation, the velocity graph here, we know the velocity is positive and decreasing, we can see. Because the velocity is decreasing, we know the acceleration is negative. And by examining the graph, we can conclude that the speed is decreasing. It's going 16, 8, 4, so on. So the speed would be decreasing in that situation. So here's the conclusion then. It says, in which situations was the speed increasing? Speed was increasing in situations numbers 1 and 2. So in 1 and 2. So to ultimately come up with some generalizations here, when the speed is increasing, the velocity and the acceleration have same or opposite signs. Should be same. Okay. Again, you only got 4 situations. In both situations where that was true, where the speed was increasing, the signs on the velocity and the acceleration were the same. So if the velocity and the acceleration have the same sign, okay, then your speed is going to be increasing. In which situations is the speed decreasing? That would be situations 3 and 4. And that would be when the velocity and the acceleration have opposite signs. Questions? No questions on worksheet 3? Okay, word to the wise, make sure you study worksheet 3 tonight. I didn't say that, but make sure you study worksheet 3 tonight. Okay, the next part here, worksheet 4. We know that speed is the absolute value of the velocity. We just did on the last part here, that if speed, or velocity and acceleration have the same sign, speed is increasing. Velocity and acceleration are opposite in sign, then the speed is decreasing. Number 4, there's 3 ways to use an integral to study motion that are easy to confuse, so watch out. It says that the integral of v of t dt is an indefinite integral. It will give you an expression for position at time t. Don't forget that you will have a plus c, which is a value to be determined by if you know the position at a particular time. So ultimately, don't forget that you have a plus c when you do that integral. So if we take the integral of a velocity function, we're going to get a position function, but it's going to have a plus c on it. So the synopsis there. If we have number 5, we have a definite integral because we have 2 limits. We have an upper and lower limit there. So the answer will be a number. Okay, we're going to get a numerical answer for that. The number represents the change in position over time, which we also call what D word? The displacement. By the fundamental theorem of calculus, we know that since v of t is equal to x prime, the integral will give us x prime at 2 minus, or x prime at time 2 minus x, or not x prime, but just x at t2 minus x at t1. This is also known as displacement, which is what I just said. So the answer can be positive or nope. Positive or nope. 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 It's negative, I'm just kidding. So it could be positive or negative depending on if the particle lands to the right or left of its original position. So if we had, if there's more negative area under that velocity curve, it'll have more of a negative direction, more movement in the negative direction, and therefore our displacement could very well be negative. And then we know that number 6, we have the absolute value of the velocity in a definite integral. So definite integral, the number represents the distance traveled. You can write total distance. I'd probably put total distance there instead of just plain old distance. So total distance traveled by the particle over the time interval. The answer should always be what? Close. Non-negative, because it could be 0. Total distance could be 0. Alright. Really the only way it would be 0 is if there was no change in time. Alright, any questions about number 4? Alright, got a velocity graph here in number 5. Looks like we have a semicircle and 2 line segments. And keeping in mind that we're looking at a picture of the velocity here, we have a velocity graph in front of us. So the values of this graph are the velocity. The absolute value of those values would be the speed. So when we want to know when is the speed of the particle the greatest, we had one of these on our test in this section if you remember. Wouldn't it be at this point right here?
Yep.
Right there, my velocity is -6, the speed would be 6. So that's the point where we'd have the greatest speed. And at which times 2, 6, or 9 is the acceleration the greatest? Keeping in mind we know the acceleration is the derivative of this picture. So at 2 the derivative is what? 0. 6 the derivative is negative something. And at 9 the derivative is positive something. So which one has the greatest acceleration? The one time 9 has the greatest acceleration. It's positive, whatever. We can obviously we could calculate that slope if we needed to, if we had to. Time intervals, the particle is moving to the left. We're always moving to the left when the velocity is negative. So we're moving to the left from 4 to 10. Like I said, this problem looks pretty familiar, doesn't it? We had this in our test when we did our chapter 5. On what intervals is the speed of the particle decreasing? Going back to our worksheet 3, speed is decreasing when velocity and acceleration have opposite signs. So velocity positive, acceleration negative. That would be from 2 to 4, well, that would be the case, wouldn't it? Wouldn't from 2 to 4, the velocity is positive because it's above the x-axis, but the acceleration is negative because the slope is negative. So 2 to 4 would be one of those cases. What about from 6 to 8 here? 6 to 8, they're both what? They're both, or 4 to 8 I should say, not 6 to 8. 4 to 8, they're both negative. So that means the speed would be increasing. And then what do we know about from 8 to 10, let's say? Velocity is negative, acceleration is positive, so therefore the speed would be decreasing. And from 10 to 12, they're both what? Both positive, so therefore speed would be increasing. Total distance traveled. Ultimately, what are we going to need to find? We need to find these areas. We need to find the area of the semicircle, the area of this triangle, and then the area of this triangle right here, huh? Okay. So if we found the semicircle, what are we going to have to do with this area when we find it? Make it positive. And then this area right here is positive, and if we add those all together, we're going to get our final answer, which should be, according to my paper here, it should be 2 pi plus 39 halves. 2 pi is the area of the semicircle there, of course, and then if you add those two triangles there together, you get 39 halves. And then what about number 6 here? It says find the value of 0 to 11 of v of t and explain the meaning of this integral in the context of this problem. So if I go from 0 to 11, and I think I said 10 to 12 earlier, that's actually only to 11, isn't it? Letters are tiny. I'm kind of old. I can't read that little one.
Yeah.
So ultimately, if I just find this integral here though, that's not gonna give me total distance, it's gonna give me what? It's gonna give me displacement. So I'd have 2 pi, negative whatever this is, positive whatever this is, add those together and that would be my displacement. Okay. So it would be the displacement of the particle on time 0 to 11. What's that answer likely gonna be like with this graph? Should be negative, shouldn't it? It's like there's more area underneath than there is above. So ultimately then the particle would be to the left of where it started. More negative motion than positive motion. Anything else on worksheet 5?
There's a number 7.
Number 6, well, if you do those calculations, it's still 2 pi for this part, and then it ends up being minus 33 halves. And number 7 actually is over here. It says that if the initial particle is 2, find the position at time 11. Well, we just found the displacement in the previous problem, 2 pi minus 33 halves. Okay. And ultimately, can't we just add 2 to that? Or add that to 2, I should say. Starting at 2, just add the displacement, and that'll give us our new position. So ultimately, that would be 2 pi minus 29 halves. Anything else about worksheet 5, example 1? Yeah.
I have a problem understanding like what 7 that's means. So that, try to put it in my head, like that's a head start, like they're at 2, and then you like.
It's just the position. If we're say the motion is along the positive x-axis or either x, it doesn't matter if it's positive or negative. Just say if it's along the x-axis,
Okay.
we're starting at 0, 2, if you will.
Okay. And then,
We're starting at position 2. Just say it's basically it's a number line. There really isn't a y component here. So at time 2, or at time 0, we're at position 2. So then, remember the semicircle's above, so we're going to the right for certain ways. And then we have the negative triangle, which means we're going back.
okay.
Okay? And then we have a little positive triangle, which means we're over here. So where did we wind up? We wound up ultimately on the other side, on the left side of where we started. All right, next one we have an analytical one. We need a calculator here. So we have a balloon, hot air balloon here. We're given a position function. And for what values of between 0 and 4 is the altitude of the balloon decreasing? Okay. Keeping in mind this is essentially motion on a y coordinate, if you will, on a y axis. And actually this gives us the rate of change, I should say. This isn't the position. So this is the rate of change here. And it's measured in kilometers per hour. So ultimately we want to know when is the altitude of the balloon decreasing. Well, if it's decreasing, then what would be the case with the velocity? Because this is ultimately the velocity that we have here. The velocity would be what?
Negative.
It would be negative. Okay. If the altitude is decreasing, it'd be going which way? It'd be going down. So whenever the velocity is negative, if you find the points here where the velocity is negative, that particular equation does not factor. So therefore, you have to use a calculator. So if we look at our graph on the calculator, we can find the 2 points where it goes to negative and then comes back to positive. Turns out to be 1.571993 and 3.51413669. You saw? So between those 2 points, our altitude function here, our velocity function here is negative, so that's where we're going down. Number 2, r prime at 2. R prime at 2 would just be the derivative at 2. Remember, like we showed yesterday, you can find the derivative of that. In this case, it's a pretty easy function to work with, but ultimately, if I just do my math 8, I do t cubed minus 4t squared plus 6, comma x, comma 2. It's just a derivative at a point problem, so it says calculator active, so we get negative 3.99. Interpret that, though, that's probably really a negative what?
4.
Knowing this is a pretty nice polynomial here, that's probably a whole number answer or some nice fraction. So again, your calculator doesn't know the derivative of that. Calculator uses an algorithm to figure that out, so sometimes there's a little bit of error. So recognize that that's not really negative 3.999, it's really negative 4. All right, and what does that mean? Ultimately, if this is the derivative of the velocity function, this is the slope of the velocity, which is the what? The acceleration. So what would the units be on that then if it would be negative 4 watts? Yep, kilometers per hour squared. Let's see. Number 3 says, what is the altitude of the balloon when it is closest to the ground during the time interval 2 to 4? Right. So let's think about when it's going to be closest to the ground. Ultimately, remember, if we look at the derivative here, we have picture here. So x cubed minus 4x plus 6. And we're ultimately looking at that curve. That's our velocity curve, and we're looking at that on the originally it was 0 to 4. We'll look at it on that window. There's our 1.5 and our 1.5 and our 3.5. That's where the velocity goes negative, right? So let's think about what's going on at the beginning of this problem here. Remember, keeping in mind that this is the velocity. The velocity here is positive, which means that the balloon is going what? It's going up. Remember, the area under this is giving us displacement, true? So what's going on with the balloon? If I were to calculate that area from 0 to 1.5, whatever that is, okay, we'd be accumulating positive area, which means the balloon would be going in the positive direction. Then what's going on with the balloon after that? It's going what? It's going down. And then once it gets to this point, that 3.5 and some change, it's going what? It's going to go back up. So the question is, what is the altitude when it is closest to the ground between 2 and 4? Well, between 2 and 4, that's going to be here and here. When is it going to be closest to the ground? At which point?
Where it crosses x-axis.
Yeah, it's going to be right here where it crosses the x-axis, isn't it? Remember, it's going down that whole time, and then what happens here? It's going to start what? Go back up. So where is it the lowest? It's going to be at that time, isn't it? So ultimately, the question is, what is our position then? Because we want to know what is the altitude. True. So we want to know what is the position at time 3.5, blah blah blah. Right. So question is, how do we do that? Well, again, we have a graph of our velocity here. And ultimately, we know that our initial position, okay, wherever we started here in this problem, and I don't know if did they even tell us an initial position?
Just gave it ground level.
It said ground level?
Oh yeah.
Yeah, so it's at ground level, so we know that the initial position is 0 here ultimately. And then this integral here, wouldn't this give us the displacement? Okay. And ultimately, what do we know about final position? It's initial position plus displacement. So therefore, that's why this is going to be our integral, and therefore we'll get 1.348 kilometers.
Wait, where's the 3.514 from? Is that
That is this 0 that we found in the previous problems, part 1, part A. Okay. So again, key issue here though is that when we want to find the final position of something, we'll start with the initial position and then we'll add the displacement. And the displacement is simply the area under the velocity curve on whatever time interval we're dealing with. That's how they got that. And ultimately, it's a calculator problem, keep in mind. So when you do this, I would not use 3.514 though. Okay. I would use every decimal that you had available to you. Like in the previous problem, we had all these numbers. So use that whole thing when you do the integral in your calculator. Don't round it. Use all the decimal places you can get. All right. And number 4. Said find the value of r of t from 0 to 4 and explain the meaning in the context of the problem. Ultimately, if this is just a calculator problem again, I mean, we could do it without the calculator because it's an easy function, but ultimately the answer here is 2.667, which is ultimately 2 2/3. And keeping in mind, know that this is just the definite integral with a velocity function, just like we explained in our previous worksheet. That's displacement. So this would be our displacement on time 0 to time 4. So ultimately our displacement would be, turns out to be, like I said, 2 2/3. So that means that also would give us our, in this case it would give us our height off the ground, wouldn't it? Since we started at 0 0. So we started on the ground. So our displacement would be 2 2/3. It would be 2 2/3 kilometers up. Okay. What about number 5? If I absolute value that, now it becomes the what? Total distance traveled. And we know the balloon went up and then it went down, then it went back up, so our answer better be bigger than 2 2/3 then, huh? And if you calculate that with your calculator, it gives you 5.779 kilometers. So ultimately, again, the actual distance traveled, since we went up some, down some, and then back up some, the actual distance traveled is going to be more than the displacement. Units of measure on both of those would be what? Kilometers. Just keep in mind that we're doing a R here is measured in kilometers per hour versus hours. So area under the curve is going to be y values times x values. Kilometers per hour times hours would be kilometers. Questions on number 2? And we had one final one. Number 6, what is the maximum altitude of the balloon during that time interval? Well, just like we did a minute ago, where are we going to hit a maximum altitude here? Yeah, wouldn't it be at the first 0? So could we do integral from 0 to that of r of t dt? Why don't we need absolute value? It's positive value, so we don't need an absolute value on that. Okay. So if we did from 0 to 1.57 or whatever that was, we get our height at that point. Notice that we do go back up here, but notice this little area right here, is that going to get us higher than we already were at the first one? Matter of fact, we're not going to get it, this is going to definitely, this positive area is definitely not as big as this area right here, so we're going to go down, however many kilometers, and we're going to go back up, not as many, so we won't get back up to that maximum height that we had, which occurs right here. Keep in mind, this is, in the scheme of velocity and acceleration and stuff, this is still highly related to what we've done before in the past, because again, we're looking at a picture of a derivative here, whether it has to do with velocity or acceleration or whatever. Okay, if this is a derivative here, the derivative goes from positive to negative here, doesn't it? What do we expect on the function when the derivative goes from positive to negative? The derivative goes from positive to negative, we should expect a what? We should expect a maximum, shouldn't we? So is it surprising that's where the maximum height is based on that information too?
Can you take the integral of 0 to that?
Yep.
Plus initial.
And your initial condition again is 0, 0 again, so it's just going to be that. So if we had an initial height, let's say we launched this thing from 15 feet off the ground, it's not going to be a feet because it's in kilometers. Or if it was 1.5 kilometers off the ground on some cliff or something, then we'd have an initial condition that wasn't 0. We'd have to factor that into all of our calculations. But all right, how about example 3? This is a numerical one here. Got numbers 1, 2, and 3 on this page. Ultimately, number 1 here, is there a time when the particle is at rest? Well, what do we know about being at rest? The velocity would have to equal what? 0. And in this case, we have the acceleration and we have velocity values here. So as both the velocity and acceleration are differentiable functions of time. And the fact that it's differentiable is leads us to some conclusions here, basically. So the velocity is decreasing from 0 to 10, and use the data table to answer the following questions. So what do we notice about what goes on between time 2 and time 6? The velocity must have what? Must have crossed the x-axis, and again, very important that we just know why. Why? Louder. The intermediate value theorem guarantees that if we have a change in y values from positive to negative or vice versa, that we have a 0 in between those 2 times. And again, that's only true because this function is one of those 2. Ultimately, it doesn't depend on differentiability, but it depends on, the actual theorem depends on continuity. But how do we know it's continuous? Because if it's differentiable, it's continuous. Okay? So ultimately, we need to know that it's continuous, and by the fact that it's differentiable, we know it's also continuous. So the intermediate value theorem guarantees that. That's your explanation. And again, when it asks you to explain something like that, you need to invoke the intermediate value theorem. If this is a question on the AP test and you don't talk about the intermediate value theorem, you're not going to get the points. Okay? So number 2. At what time indicated in the table is the speed of the particle decreasing? What do we know about decreasing speed? Speed would be decreasing when velocity and acceleration are opposite, so that would be at time 2. Time 2, the velocity is positive and the acceleration is negative. And number 3, left Riemann sum to come up with an area from 0 to 10 and explain the meaning of that integral. So left Riemann sum, we notice that we don't have uniform subintervals here. So our first one would be 2 in length. we'd use 5 for the height. So we're doing left endpoint. Then the next one would be 4 in length. We'd use 3 for the height. Then 4 again, and -1 for the height. And if we add those 4 rectangles together, we should get 18. So again, we got 2 in one direction, 5 in the other for our first rectangle, 4, and then 3, so 12 there. 4 and -1, 4 and -1 make -4. Add that all up, we get 18. But more importantly, what does that mean? That is the what? It's the displacement. Seeing the same problem over and over again, don't we? Alright, and last few parts here are on this page, I guess, here. Looks like we missed a little spot on this one here. Yours turned out that way, I think, too. But the approximation in part 3, is it greater or less than the actual value? If we use left ram, and this is a decreasing function, we know that that's always going to be, those rectangles we draw are going to be above. So therefore, that would be an overestimate that we found. Okay. And again, because when we have a decreasing function, LRAM gives us an overestimate always. Number 5, find the absolute value using the trapezoidal approximation and show your computations and so on. And I'm going to go back to this one. We'll do the meaning part. The meaning part, of course, is the total distance traveled. Okay. We'll do the computation in just a minute. We'll go back to that one. I want to make sure we see the picture of that. Number 6, determine the value of the integral of a of t and explain that meaning. A of t, of course, if we want to find the value of that. And here's a good example. Ronnie doesn't say which method to use, right? So you can use basically whatever you want. So they chose to use the, well, I guess you really don't need, actually you can just, we know that the antiderivative here is v, and we know values of v, so we could actually calculate it using the v values we have, because we know a v of 10 and we know a v of 0, don't we? So again, antiderivative of a is v, so it would be v at 10 minus v at 0, so ultimately that would be -8 minus 5 would be -13. And what would the meaning be here? If it's meters per second squared times seconds, it'd be meters per second, wouldn't it? So that would be a velocity. And ultimately, it would be our change in velocity, if you will. Okay. And think about why it's also change in velocity. If the answer to this is v of 10 minus v of 0, isn't that the velocity at 10 minus the velocity at 0? Isn't that the change in velocity? Alright, so let's go back to this number 5 here, because I want to picture, if we're going to do the absolute value of v of t here, and we want to do that with the trapezoids, okay, keep in mind that when we graph this, draw my graph down here for this one, our v values are 0, 5, that's right there, then we have 2, 3, so we'll say that's right there, and then we have 6, -1, but if it's 6, -1, what's going to happen to that -1? It's going to become +1. Okay? And then my 10 was -8, so that means I'm going to have 10 what? 10, 8. So when we draw the picture of that, instead of drawing it normal with the values below, we're going to draw those negative values above. And so once we have that drawn, now we can draw our trapezoids. So we'd ultimately have 3 trapezoids as such. And those trapezoids would each be a half times the height here on this side. The height here on this one is 2. Okay, and the 2 bases are, this is up 5 and this is up 3, so that's how they got this part right here. So there's your trapezoid formula for the first trapezoid. It's 2 because this is a height of 2. The bases are up 5 and up 3 here. The second one, we got a half times, this is 4 of course here. And then the heights are 3 and 1. 3 up here, 1 up here. So there's our second trapezoid that we have pictured below. And then our third one, of course, is a half times 4 again, just because it goes from 6 to 10. And then the heights here are 1 and 8. And there's our third trapezoid. And so again, ultimately that corresponds to that one, and that to that one. And if we add those all up, we get 34. And in this case, that represents 34 kilometers, I believe, right? Actually, did they give us a unit in this one? No, no units in this one, so it'd be 34 whatever units in terms of distance. Could be kilometers, miles, feet, whatever the case may be. Alright. Questions on number 5? Anything else on example 3?
Was number 6 like displacement?
No. Remember, it's the absolute value. It's the integral of the acceleration, which is the velocity at time 10 minus the velocity at time 0. So wouldn't that just be the change in velocity? So ultimately, it would be a velocity because it's just a change in velocity. So the units on there here again are kilometers per second, or meters per second, or miles per hour, or whatever the case may be. Okay, that's that. So we had actually we had one more on there, right? This page.
Yeah, making connections.
So for this one, the we have a observer recorded the speed for the race car, approximately how far east did the car travel over this 6-minute time interval. So we're traveling here. Wants to know, this final question here is approximately how far east did the car travel over this time interval? Well, if we have the speed here, it says draw a plausible speed graph. So we can, of course, just graph these points and we can draw a curve through it, a curve through those points. All right, and it says solve this problem from a graphical perspective without using integrals. In other words, okay, if I were to have these points plotted, okay, how many different ways are there that I could calculate the area under that curve, which would give me my distance? I could do LRM, IRM, MRM, trapezoid, Simpsons. Okay. Since we do have a uniform subinterval here, I could use either the trapezoid or Simpson's rule. More difficult to use Simpson's rule if we don't have uniform subintervals. Okay. In fact, we generally never would use that if we don't have uniform subintervals. Okay. So we can calculate that. Again, just use any of those that you want to. Determine a possible speed function and solve this problem from an analytical perspective. If you look at this, it goes from 0 to 90, it goes up to 135, and then kind of back down. What kind of curve might this be if we were to draw it? Maybe a parabola. Okay. So we could write across. You know, this is kind of an open-ended question because if you did something other than a parabola, you might have a different model that might be a little better. Maybe if you used a cubic or something, you know, or whatever the case may be. But bottom line is, if you used a parabola, could you write an S equation for this with your calculator? Put these in your stat edit and do quadratic regression. Get an equation for it. And once you have that, then compute the value of this that you found in your previous part. So just in terms of meaning, what is this going to mean if you do 1 over 60 times the integral from 3 to 4 of that? Yeah, keep in mind that that these are in the time here is in minutes, right? So just this part right here would give you the displacement over the 3 to 4 minute time frame. True. And if you divide it by 1/60th, we would ultimately get the result here would be, actually, let's think about what the units would be on this. If we went from 3 to 4 of our S function here, keeping in mind that our S function is going to be measured in, I guess here's what the issue is from above. If we look at the units on here, we have miles per hour versus what? Versus minute. That's why we have 1/60th here. Because ultimately, in order to get the units to cancel out right and actually give us an average value of the S function, if you will, okay, we need this to be translated to hours, if you will, instead of minutes, okay, in order to cancel out the hours.
So if it was ours, just get 1, right?
Yeah, if this time was measured in hours, then it would just be 1 over 1, right? So it needs to be 60 because of the unit issue. All right. So again, the integral itself here gives us the displacement, okay, and then to multiply it by 1/60th, which is a unit of time on the bottom, would get us back to a velocity again, then, wouldn't it? Okay. So ultimately, wouldn't it be the average speed over the time 3 to 4? Right.
What if you like changed it to like minutes? Or yeah.
Well, you could change all these speeds to miles per minute if you wanted to.
Yeah.
You could do that if you wanted.
And what would that do if I did that?
Well, then your integral here would just be, you know, you'd have 1 over 1 again then. If you changed all the units to minutes here and you went from 3 to 4, it'd be 1 over 1.
Then your function would
Your function would be a different function too altogether, but you'd ultimately get the same answer either way. Okay. Alright. And then a plausible distance graph here on this one. a distance graph. Remember, ultimately, the distance traveled here, since these are all positive values that we're working with here, the distance traveled is just going to be the area under the curve from 0 to 0, 0 to 1, and so on. We can go through and find the distances at each of these points. So if we do from 0 to 1 of our curve that we have here for us, okay, we would have the distance traveled. We could make points for that. So if we want to find x of 0, okay, x of 1, x of 2, and so on, and plot those, we can get our distance graph. And then finally, in the number 2 here, it says, Anna accompanies her mother on a trip to the grocery store, keeps the car's speed at 10-second intervals. Explain how she can use the data to estimate the distance from her house to the store, and what is the connection with this process in the definite integral. So bottom line is here, if she calculated the mom's speed from 10-second intervals all the way to the store, okay, couldn't she just find the area under the curve that those points would make? Okay. Keep in mind these would be all positive value because we're only going in one direction. We're going from home to store, right? So if she calculated all those speeds, she could find the area under that speed curve, and what might she use to do that with? What would probably be the best way for her to do that? Simpsons or trapezoid? She just basically have a data table that look kind of like this, wouldn't it? Okay. All right. And ultimately, what's the connection between this process and the definite integral? Okay. Well, if I wanted the actual total distance traveled, okay, I would write the definite integral from 0 to whatever, however long it took her to get to the store. Okay. And ultimately, that trapezoid or Simpson's approximation that you calculated is just an approximation for the definite integral, then, isn't it? All right. Excellent questions. Excellent AP questions. If you are in good shape on that, then you a lot going for you at this point. Okay? All right.